When we consider the inverse transform of this 2s plus 4, notice the numerators are rarely the most important thing. The denominator, s squared plus 2s plus 5, is going to be the key ingredient for identifying which element of the table makes sense. Now the problem is, we can't factor this. That would be our first approach, is to try to find linear factors. We can't seem to do that here. We could try. We could try to use the quadratic formula and find the roots, or we could try to guess and check factors. But at the end of the day, there's no real root that'll satisfy this denominator here. We can't factor it into linear real factors. However, we've seen some inspiration with the exponential times sine and cosine, that if we can make this look like, as a goal, something over s minus a squared plus k squared, then we're going to be in business, because that transforms, because of the s minus a, to an exponential. And then we have the k squared. It could be either a cos or a sine of kt on top. So let's see how that plays out. To get this form here from what we had before, the technique we're going to use is called completing the square. And most of you have seen this before. Again, if you need a refresher, this would be a good time to get it, because this will be a commonly used technique. We're asked for the inverse of 2s plus 4 in the numerator. We leave that alone for now. The s squared plus 2s plus 5, this is where we're going to get things a little more interesting. What I like to do is recognize that completing the square means getting rid of this s term. So what I want to do is get a complete square for that. Well, the way we get a complete square there is by adding 1, because that would give us s plus 1 squared. We take this factor here in the middle, we divide by 2, and then we take the square of it to put it here. If that's a little hazy, by all means take a look at some of the great online guides for completing the square. Now, we can't just go willy-nilly adding plus 1. We had a plus 5 before. To make things balanced, we have to include a negative 1 as well. What is that going to let us do, though? It's going to let us group things. We can group these three terms here. That'll give us the inverse of 2s plus 4 over this grouped is s plus 1 squared. And then we can group these two terms here, 5 minus 1, and get a plus 4 out of that. Now we have a match. We have a form that is exactly the form that's going to give us an exponential times coses and sines. Now there's still one more wrinkle. We'll look at that on the next page. From this form, recall that if we're going to have a shifted cosine, let's say e to the at cos of kt, the transform of that is going to look like s minus a over s minus a squared plus k squared. When we transform the cosine, which has an s in the transform numerator, we're going to need to replace it as well as the s in the bottom with s minus a. So how does that play out here? Well, we need to gather some terms and make it look more and more like this form here. So we'll have the inverse of, we definitely know we have an s plus 1 squared plus 4, and then we have two s's here, but we know we need s plus 1's. So what we just did there is we have an s plus 1 now with a 2 multiplier, that's fine. We just effectively added 2 to this total, so we're going to need to subtract 2 as well, and then we have the original plus 4 still available to us. Well, what does that give us? Let's make this as linear as possible. We'll bring the 2 here out front, and then we'll have s plus 1 over s plus 1 squared plus 4. That is an exact match to the inverse of the cosine times an exponential. What about the remaining coefficient here in the numerator? Well, we can write the inverse again. We can take that same value, which is negative 2 plus 4, that's plus 2, over s plus 1 squared plus 4. That denominator was common. And then we ask, well, what would the transform of a sine function look like? The transform of a sine function, e to the at sine kt, would look like Keep in mind the transform of the sine. Look it up in your table if it's not completely at your fingertips. It's k over s squared plus k squared. And so if we have a 2 squared in the bottom here, which is exactly what we have, we need this 2 on top to have the transform that we're looking for. Oops, one ingredient missed. We need to have the s minus a squared there. So if I was looking for a transform of an exponential times sine, I would need s something shifted squared plus a k squared plus that same k value on the top. That's exactly what we do have. So now we have an exact match between both terms that we're trying to invert. So now we can complete the inverse. We have a coefficient of 2 out front. We said the inverse of this would be dictated by the original exponential cos kt. The exponential we're going to get, it's s minus minus 1, so it's e to the minus t times cos of our k value here is 2, so cos of 2t. And the next term, we said was an exact match to the same exponential, e to the minus t, times the sine of 2t. And that's the full calculation that will let us expand out a quadratic denominator like this and get to terms that we can individually transform back to these shifted or exponential times e, cos, and e times sine.